Okay, so today I'm going to basically be discussing some details when we want to actually make variables, and I'm going to be discussing the kinds of variables and specifically some concerns about precision. So I'm going to go and make my new file here. Call it kind.f90. Again, we'll just go ahead and make a new program called kind. And then we will write our implicit none. Okay, we're going to start like we did last time with just making a real variable x. And we'll assign x the value of 1.0, and then we'll print x. So we write the file. I'll go ahead and compile it. Then we execute it here. All right. So no issue. But we notice that there's, let's see, there's 1, 2, 3, 4, 5, 6. There's 8 trailing zeros here. So if we go back into the file here, we can go in and we can give it a kind argument. And basically this kind argument is going to be describing the type of, the way we want to store the value in the computer and how much space. You can kind of think of it, how much space do we want to give to that variable? Because in reality, there's a finite amount of space to store each variable inside the computer, and we have to decide how much we want to do that, or how much space we want to provide for it. And the reason there's this kind argument, from what I've been reading, is used to in older computers, there wasn't a standard way to allocate this information. So on the compiler step, there's sort of a conversion of the kind argument to what kind of float value or what kind of numerical value you want to store. So a good source, and I'll just kind of quickly go over some sources here. So here is the Fortran, GNU Fortran compiler information that tells you what the kind arguments mean. So you can give a kind for each type of variable. And in the case of real, you have 4, 8, 10, 16. And this corresponds to the number of bytes that in the computer that will be available, I guess, for that variable. So we have 4, 8, and then 10 and 16 bytes. And remember, 1 byte is 8 bits. So it's just a number of spaces that we can actually store information into. I'll kind of be popping back and forth over here, but a good explanation of kind of some of the background as to why these kinds are why this is used is available here. This is from a slide deck from Professor, let me see here, Randall at Colorado State University. Here, this is the Fortran wiki, and we'll get back to this in a second. But in addition to amount of space that we're going to store, we also need to decide what precision we want calculations to basically be done with that number. Let's see here. Yeah, and then I came across, this is from the University of Hawaii. So this is presumably from a class. I'm not sure who made it, but they have several lessons, and specifically lesson 3 has a very good talk of basically why you need to set precision and some of the issues that you can run into. So this is another good resource. Okay, so coming back to this, let's go ahead and make 3 different variables to show what the effect of setting different kinds are. So let's see here. So I'm going to set 4 different sizes here. Of course, I have to name them different things. Okay, then we'll come down here, print them out. So let's compile, run it. and here you kind of see this idea. So as we allot more space to the number, we can store more, decimal points afterwards. Cool. But let's see what happens when we go ahead and change. Instead of 1.0, we go to 1.1. Okay, so immediately we see something you might not expect, and that's basically you have you have kind of these random numbers popping up, but they're not random. It's basically a result of the computer needing to convert between our system of telling numbers, so the usual system, which is base 10, to the computer, which is in binary, which is base 2. So it has to convert your input into binary and then spit it back out to you back in base 10. And there are numbers that basically depending on how you go about calculating that, you can get this error. Now, it's all a matter. The question it's all a matter of, does that matter to you? And it depends on what you're trying to do. But if you're not careful about it, that error can add up over time, over many calculations, and then cause you a problem. So we'll go ahead and see how to work with that. So let's see here. If I come back into the file. So we'll keep the kind the same, but now we're actually going to assign a different kind of number into that open space. So again, the kind, we're going to still be using reals, and the kind will kind of give us the space, but now we're going to in essence, give it a different kind of number called a double precision. And it's honestly, I don't know the details of the actual difference, but you can kind of think of it as a more accurate representation, as a higher precision. However, it requires twice the storage space. So that's kind of the trade-off. So if we go ahead and assign here, so this D is going to tell us that it's a double precision. And then the 0 is equivalent to scientific notation, where you might have, basically it tells you how many powers of 10 to multiply it as well. Since it's 0, it's 10 to the power of 0, which is just 1. So it's not going to shift where the decimal is, but the D tells us that it's a double precision. So let's go ahead and... Okay, so immediately we see that we still have some error with we still have some error with the associated at the end, but now we don't get all of this junk, these random numbers here. But for something as large of an open space here, we need to use a higher precision to kind of avoid that occurring. So we need to use quadruple precision. So all the real fix to kind of these issues is, instead of worrying about kind and doing it how I showed you, you want to go ahead and we want to go ahead and basically not worry about what the compiler is doing with the kind, because again, that's compiler specific. We're going to go ahead and define some variables that, so we come over to the Fortran wiki. We have where we can actually define our, both the precision as well as the range of numbers that it's going to pull from. So again, 32 bits, 64-bit, 128 bits. The number of bits, it sets the range by which you can pull the numbers out of. So by go ahead and just doing it ourselves, so I'll just copy this over. Here we go. So we now have access to, we've defined these variables, these parameters, and the parameter change, adding in this parameter here just means we can't redefine it later in the code. But the parameter, this SP, any number that we associate with SP will now be single precision. Any number we associate with DP will double precision, and then again, quadruple precision for here. And again, same for integers. So let's go ahead and just do that. So instead of having a kind, we're going to pass just the argument of the, in this case, we'll just do single precision for these. We'll do single precision, quadruple, or double precision, and quadruple precision. Okay, and then instead of doing this D0, we do an underscore and associate it with the kind that we want it to be. Associate it with this type of precision that we want to be. Okay, and again, you can already see, you know, when you coming out of the world of Python, you don't have to. I mean, you do come across worrying about this, but a lot of times you don't really need to worry about this sort of thing. But for scientific program, trying to be precise, this will end up mattering, as we'll see, you know, down the road. But so I'll go ahead and save that. We'll recompile. And there we go. So now we see that we get accuracy all the way out to, you know, as far as this size is allowed, as far as the 64-bit and 128-bit kinds are allowed. So again, there's still rounding error, but now it's much less. At the, you know, depending on what size, what precision you use. So, yeah, I think that's pretty much all I wanted to cover. Now you can do the same thing for complex variable types, for integers, and then it's a matter of what trade-off you have to trade off between accuracy and then amount of memory that you're going to take up to do it. Okay, thank you for listening.